So today, our new method of integrating some functions is what we call inverse substitutions, or sometimes trig substitutions, which makes sense because they are trig substitutions. And so, as a general rule, whenever you see one of these three things here, root a squared minus a squared, root a squared plus x squared, or root x squared minus a squared, you're going to want to make one of these substitutions for x. So if you have a squared minus x squared, you want x equal to a sine theta. If you have the plus, you want to make it tangent. If you have the minus with the x squared first, you're going to want to make it secant. And so let's first off talk briefly about why we can make these substitutions and why it helps and why it works. And it works because of trig functions. So let's think about just the first one here. Here's theta with a right triangle. If x is equal to a sine theta, I should really draw this triangle up a little higher so I have room to write. If x is a sine theta, that tells you that sine theta equals x over a, right? Which means that the sine of theta on a right triangle should be x over a. And what does that give us for this third side over here?
The square root of a squared minus x squared.
Right, which is exactly what we're substituting out. And this term is an annoying term to try to integrate, but a sine theta itself is not an annoying term to try to integrate. That's actually very easy to integrate, right? And so substituting out the annoying thing for something simple allows us to use this right triangle in the end. Once we're in terms of theta, once we've integrated in terms of theta, it allows us to go back into terms of x that we started with. Okay, so same thing here with this one. This one gives us tangent theta equals x over a, right? Which will give us a nice little right triangle here. Pretend that's a right triangle with, like I said, x equals, or tangent theta equals x over a, which gives us a hypotenuse, root a squared plus x squared. And the last one over here, if we had this one, this would tell us that secant theta equals x over a, or secant is x over a. That ought to be like this, which gives us root x squared minus a squared for an opposite of it. Okay? And so that's sort of the the base reasoning behind why these substitutions work. We're just going to turn a bunch of crap with x's in it into something much simpler, hopefully, with thetas in it, and then integrate in terms of theta, and then come back and get an answer back in terms of x by using these right triangles. Make sense?
Yeah.
All right, cool. Now, a couple of things. First off, it's not always easier to do the substitution. Sometimes you might have something in there that you can just use a simple u substitution, and it might be easier to do that. And it doesn't specifically have to be inside of this square root. Suppose I just had, let's say, maybe I had x squared minus a squared to the 3/2 power. Well, there is a square root within that. And so we could just make that, this thing cubed, right? Right. We could make the same substitution and then have to cube it. Does that make sense? If it was to the 3/2 power. We could even do the same thing if it wasn't inside of a square root, right? If it wasn't inside of a square root, it would just be the square root squared. And so then we would just do the same substitution with the thing squared. Does that sort of make sense? Yes, no, maybe. So it doesn't have to look exactly like this. It just needs to be in a form very similar to this. And it won't always be easier, but most of the time it will be. So let's take a look at this. The integral of root 9 minus x squared over x squared. So based on what we just looked at, what substitution do you think we should use for x here?
3 sine theta.
3 sine theta, exactly, right? So it's a squared minus x squared, right? We'll call this a squared minus x squared. So a is equal to 3, right? Root a squared minus x squared gives us a equals 3. And so x should be 3 sine theta. Everybody good with that to start with? Okay. So then we'll just plug that in. Everywhere we see an x, we will replace it with 3 sine theta. So we'll have an integral of the square root of 9 minus, what's x squared? It should be 9 sine squared theta. And then all over x squared, which is 9 sine squared theta. Yeah. And then what's the issue that we've got here is we've got a dx, right? Well, we can't integrate something in terms of theta if it's got a dx attached to it, can we?
No, we cannot.
No, we cannot. So what should we do? We should figure out what dx is equal to by taking the derivative of x. What is dx equal to?
3 cosine theta d theta.
3 cosine theta d theta. And so we will attach to this 3 cosine theta d theta. And so now we have something all in terms of sine and cosine, all in terms of theta, right? With a d theta attached to it. And so we should be able to integrate this really, really easily now. Doesn't it look really easy to integrate? The answer is yes, yes, it looks exceptionally easy to integrate because we're going to simplify it down. So first off, and we're going to start doing some of this simplification a lot more quickly soon. But for now, we're just going to, kind of write out each of the steps. So we have a 9 minus 9 sine squared theta. What can I factor out of that?
9.
9. And if it's a square root of 9 times square root of 1 minus sine squared theta, I should be able to pull the 9 out of there, which makes it a
3.
3. So we're going to have a 3 times the square root of 1 minus sine squared theta times 3 cosine theta d theta all over 9 sine squared theta. And we should see from there that I can cancel out the 3 times the 3 divided by the 9. Yeah?
Yep.
And now we can take what's inside of that square root and rewrite it and then simplify it. So what can I rewrite 1 minus sine squared theta as?
Cosine squared theta.
So we got a square root of cosine squared times cosine over sine squared d theta. Everybody good with that? And what's the square root of cosine squared?
Cosine.
Cosine. And times cosine is another cosine squared, right? So we got cosine squared over sine squared, which is now just an integral of cotangent squared theta d theta. And how do I integrate that? This is the easy part. Cotangent squared can be rewritten as cosecant squared minus 1, can't it? Can't we rewrite cotangent squared as cosecant squared minus 1? Yeah, which gives us what? What's the integral of cosecant squared?
Negative cotangent.
All right, so we got negative cotangent theta and then minus What's the integral of 1 d theta?
Theta.
Okay, so minus theta plus a constant. And is that our final answer?
No.
No, we got to go back in terms of x. So we made the substitution that x was equal to 3 sine theta, right? We said x is 3 sine theta, which tells us that sine theta equals x over 3, which makes this side √9 minus x squared, which is that thing we subbed out at the beginning. And so now we'll go back down and say, well, what's the cotangent of theta? So cotangent of theta ought to be adjacent, right? Over opposite. And then minus theta. Well, what's theta in terms of x? Sine theta ought to be x over 3, so theta ought to be
Inverse sine x over 3.
inverse sine x over 3. So we have negative √9 minus x squared over x minus the inverse sine of x over 3 plus our constant. Good or no?
Can you go back one slide to the other one?
Sure,
Okay, thank you.
no problem. Everybody good here and now? Any questions, any issues with this? All right, let's do another one. Any thoughts? What should we do here?
Substitute x squared plus 4 for 2 tangent theta.
All right, so we're not substituting out the full x squared plus 4 for 2 tangent theta. We're just going to substitute the x equals 2 tangent theta. But yeah, that's exactly what we want to do. So what does dx equal then? Should be 2 secant squared theta d theta. So we should end up with an integral of 2 secant squared theta d theta over 4 tangent squared theta square root of 4 tangent squared theta plus 4. Everybody good with all of these substituting in there? Or no?
Yeah, that all makes sense.
All right, cool. So let's now then try to simplify as much as we can. So first off, we can pull a 4 out of the square root. As we pull the 4 out, it becomes a
2.
2. The 2's will cancel. And so we're just left with a 1/4. So let's put that 1/4 outside the integral. And all the other constants are gone. So we've still got a secant squared theta d theta in the numerator. And in the denominator, we've got a tangent squared theta times what? We took the 4 out of this, so this became tangent squared plus 1, which is
Secant squared.
secant squared, and the square root of secant squared ought to be
Secant.
secant. So we've now got 1/4 the integral of secant squared theta over tangent squared theta times secant theta. So we can cancel one of the secants, right? Give us 1/4 the integral of secant theta over tangent squared theta d theta. And what can we do with that? What was that?
I was gonna say, can you change the tangent squared theta into secant squared theta minus 1?
Okay, we could turn that into secant squared minus 1. And where do you want to go from there?
I don't know, I didn't think it through, that's why I didn't finish my sentence.
Yeah, so I mean, we could turn tangent squared into secant squared minus 1, but generally, once we've got it down to just trig functions with no other constants, we want to try and keep it that way if we can find a way to integrate it without changing it, especially without changing the stuff in the denominator. So let's see if we can find a way to rewrite this so that it's easier to integrate in just the form it's in without changing it to other trig functions with constants. So we can change them to sines and cosines or something like that, but maybe not using the Pythagorean trig identity. So let's go with calling this 1 over cosine over sine squared over cosine squared d theta. And if we simplify that down, what does that give us?
Cosine over sine squared.
Cosine over sine squared. So let's stick with that. And how am I going to integrate this one?
U sub.
Okay, what do you want to sub out?
I think sine squared. Or, well, just sine.
Just sine sounds better. If u is sine theta, then du is cosine theta d theta. And so this ends up becoming 1/4 of the integral of, let's see, cosine theta d theta is du, right? Du over u squared, which is just a power rule, right? That's just u to the -2. So that should give us 1/4. What's the integral of u to the -2?
-1 over u.
-1 over u and then plus our constant. So we've got -1 over 4u. So that would become -1 over 4 times sine theta. Yeah. Everybody good with that? Plus our constant. There's theta, right? And we know that tangent is x over 2. So using the Pythagorean theorem, it should be root x squared plus 4. And so our sine value should be what?
X over the square root of x squared plus 4.
X over the square root of x squared plus 4. So we've got -1 over 4 times x over root x squared plus 4 plus our constant. And it might be nice to not have a fraction there in the denominator and just throw this up into the numerator. So I guess a new page here real quick. That could become -root x squared plus 4 over 4x plus our constant. Good or no? I'm just flipping that around. Everyone okay with that or no?
Yeah. That
Cool.
one was simpler.
Simpler. Wonderful. Let's do another one. You guys want to try and do this one on your own?
Yes, please.
All right, ready, go. All right, we all done?
I'm chilling.
Does that mean you're done?
Yeah.
All right. So what did you guys do? What was your first step?
Do the substitution.
What substitution did you do?
X for x, and then it turns into a tangent theta.
All right, is that what you guys all did? Was x equals a tangent theta or 2 tangent theta? Or what is it? No, just tangent theta for this one? Yeah.
I did just like a normal u substitution where u
Ah,
equals-
good. That's what I would have wanted to do here. Just a u substitution. Let's let u equal x squared plus 4. du is 2x dx, 2, 1/2. 1/2 the integral of u to the negative 1/2 du, which ought to give us 1/2. That's not that 1/2. 1/2 of what? 2 root u plus our constant, or root x squared plus 4 plus our constant. That's probably a lot quicker than doing it with the trig substitution, yeah?
Yeah.
Yeah, let's do it with the trig substitution also, just for fun. This is why I was saying it's always good to look and see if there's a nice simple u substitution to use, and in this case there was. But just for the practice, let's do it the other way also. So we had the integral of x over root x squared plus 4 dx. That was our original problem, I believe. And so if you'd done with the trig substitution, you would have done x equals tangent theta. No, sorry, 2 tangent theta, yeah. And dx would be 2 secant squared theta d theta, which would give us an integral of x and then dx over root x squared plus 4 for tangent squared theta plus 4. So for those of you that did the trig substitution this way, is that what you started off with?
Yes.
Great. All right, so we factored out the 4, pulled that 4 out, which became a 2 down here, right? Cancels with one of these 2's, and the other one we can pull out. So we'll make this 2 times the integral of, and then let's see what we got left here. Well, we'll write it out. Tangent theta secant squared theta d theta over, this one became tangent squared plus 1, which was secant squared, and we square rooted it to get secant. And so this just became 2 times the integral of secant theta tangent theta, which that one's an easy integral, right? What's that one?
secant theta.
So we got 2 secant theta plus our constant. And secant theta, if we look at the right triangle, right here is x over 2 for tangent theta, root x squared plus 4 here. Secant ought to be hypotenuse over adjacent. So this just becomes 2 root x squared plus 4 over 2 plus our constant, or just like we got the other way, root x squared plus 4 plus c. Good or no?
Yeah.
Cool. Any issues with that? Everyone feel okay there? With all we've been doing with the trig subs so far? Let's do another one. So what will our substitution be this time?
A secant theta for x.
Yep, so we'll have x equals a secant theta, and dx will be a secant theta tangent theta d theta. Yeah? So in our numerator, we just have dx, which is a secant theta tangent theta d theta, over a squared, or square root of a squared secant squared theta minus a squared. And what does that give us? First off, we can factor the a squared out and pull it out of the square root, which gives us what? Just an a, right? Which will cancel with our just an a right there. So we have no constants left. And then we got secant theta tangent theta. And then this is secant squared minus 1, which becomes what?
Tangent squared.
Tangent squared, and then we square root that to become tangent, which will cancel with the other tangent. So effectively, all we end up with here is just an integral of secant theta d theta. And we should know that one. We proved that one just the other day, right? That's what? What's the integral of secant theta? You've memorized it now.
Natural log of secant x plus, wait, no, the natural log of absolute value secant x plus tangent x.
In this case, thetas, right? Instead of x's. Good. And I'm going to call this constant 1 over here, just for fun. All right, so let's figure out what secant theta is and figure out what tangent theta is using our right triangle. We should already know what secant theta is, right? Because that's given to us. Secant theta is x over a, which makes this side root x squared minus a squared. And we've now got natural log absolute value of secant theta, which we know is x over a, plus what? Tangent theta, which should be root x squared minus a squared over a, all plus our constant. Is that a good answer there?
Yeah.
Yeah, that's a good answer. Is it the best answer? No, it's not the best answer. Oftentimes what you'll see, and you'll want to kind of keep an eye out for this on problems on the AP test, especially in like multiple choice where they give you multiple choice answers, is that since these both have the same denominator, they could be written together. Right? And then what do log rules tell us? It tells us that if I have the log of something divided by something else, I could rewrite that as the log of the first thing. Minus the log of the second thing. And what can you tell me about the negative natural log of a? What can you tell me about a? What is a?
It's a constant.
Right, a is a constant, so the natural log of a is a constant. So all of this is just some constant. So it's entirely possible that an answer on the AP test might look more like this rather than this. And so just be cognizant of that fact that if those have the same denominator, you can put them together, one fraction, separate the logs, and that natural log a that's a constant can just be thrown in with the other constant to be some other constant. Does that make sense?
Yeah.
All right, cool. All right, how are we feeling so far? We're feeling good? Hopefully none of this is too awful.
I'm feeling like I'm going to need to practice this a lot.
Oh yeah? Okay, good. I'll make sure to give you lots of problems. Don't worry, we're going to do a bunch more today also. We're going to start with this fun one. We're going to figure out the area of an ellipse. And that was you, right? Noah, that was saying I need to practice a lot more.
Yeah.
Okay, good. The good news is, I guess maybe it's not good news. The bad news is that they get a lot more difficult than the ones we've done so far. So maybe that's bad news for somebody that feels like they need a lot more practice. But there'll be lots more problems to practice with, especially when they get more difficult. Exciting. All right, let's find the area of the ellipse. Sound good? Yeah, it sounds good. What does this ellipse look like to start with? It's got an axis, a major axis of, well, we don't know if it's a major axis. I guess we just have an axis that's got a length of (2a), right? And then another one that's 2b. Right? An ellipse that looks like this. Okay? We want to find its entire area. And this is an ellipse that's centered at the origin, right? Yes, this is an ellipse that's centered at the origin. So it might be easier than, if we wanted to find this entire ellipse, it might be easier to just find one piece of it and then multiply it by 4. Yeah. Or no.
Yeah.
Yeah. All right, so let's see if we can use an integral to find this area from 0 to a. So we're going to try to find an integral from 0 to a of something. Well, what do we need to do with our original ellipse equation before we can write out our integral?
Probably need to put y in terms of x if we're going to do it on an integral from 0 to a.
All right, so yeah, so we'll say y is equal to what? Y is equal to the square root of, let's see, that should be 1 minus x squared over a squared all times b squared. Yeah. 1 minus x squared over a squared times b squared gets you y squared, and then square root it for the y.
Yeah.
All right, cool. First off, that b squared that's inside of there seems like I don't really need that to be there, right? I could pull that out of the square root as a b. And what is b? B is just a constant, right? So what should this integral become? What constants do we have out in front? We have a b.
Times the integral from 0 to a of the square root of 1 minus x squared over a squared.
All right, and did you say 4b or no? I couldn't tell if you said that.
I don't believe I did.
All right, so yeah, there's just a b, but since we want 4 of these, we're just going to put a 4b out in front of it. So this integral right here should tell us the area of an entire ellipse, no matter what a and b values we have. Do you all agree with that?
Yeah, it should.
It should. It seems like it should. All right, so let's see if we can do this then. 1 minus x squared over a squared looks kind of annoying. Could I simplify that down a bit? If I multiply the 1 by a squared over a squared, that'd put an a squared minus x squared over an a squared, right? And if I have everything over a squared, I could pull out a 1 over a squared from the square root, which would be a 1 over a when I pull it out of the square root. And since a is just a constant, I could put that out in front. All right, dx is here. You guys agree with that? Getting a common denominator and pulling out the a?
Absolutely.
All right, cool. And now this is in a nice little form where we should be able to do a
Inverse
substitution, right? So what should x equal?
a sine theta.
Okay, so if x is a sine theta, then dx is a, as a horrible looking a cosine theta, d theta. And so that should turn our integral into 4b over a times the integral of, well, now we've got square root of a squared minus a squared sine squared theta times dx, which is a cosine theta, d theta. And what has to happen when we go from x into theta?
Change the limits of integration.
Change our limits of integration. So if x was 0, that's going to give us 0 equals a sine theta, or sine theta equals 0, which would give us theta equals
0.
0. So we'll stick with 0 down there. And if a equals a sine theta, that would give us sine theta equals 1, which would be at theta equals pi over So we should now have an integral 4b over a times an integral from 0 to pi over 2 of all this junk we got there. Good or no?
Groovy.
Wonderful. All right. First off, the a here and the a here should cancel each other out. True? Yeah.
Yeah.
This is true.
All right. And then the a squared minus the a squared there, though, you can factor the a squared out of that and pull it out of the square, which just gives you an a, which can go out in front. So 4ab times an integral from 0 to pi over 2 of the square root of 1 minus sine squared, which is
Cosine squared.
so square root of cosine squared, which is just cosine times another cosine, which should be cosine squared theta d theta. Good or no?
Cool.
All right. How do we integrate cosine squared theta? Good thing we talked about this a couple days ago.
Using the power reducing formula.
All right. So the power reducing formula says it should be 1/2. So I'll just pull that 1/2 out right now. And then the cosine squared turns into 1 plus cosine 2 theta d theta. Good or no?
Yeah, good.
Okay, perfect. So then all we got to do is simplify our outside and integrate our inside. Integral of 1 d theta is theta. And integral of cosine 2 theta d theta is minus, no, not minus, plus 1/2 sine 2 theta. Evaluated from 0 to pi over 2. And since this was a definite integral, we don't have to worry about switching back from theta into x. We can just evaluate at 0 and pi over 2, which ought to give us 2ab times pi over 2 plus, that's 1/2 the sine of 2 theta. That's 1/2 sine of theta. Sine of theta is, sine of pi. Sine of pi is 0. And then minus, if theta is 0, that's 0. And then it's also 0. So what do we end up with? We end up with the area of an ellipse. The area of any ellipse should be found by multiplying pi by a times b. Look at that. We've derived the formula for the area of any ellipse. Isn't that exciting? Just using a small amount of calculus.
Any ellipse centered at the origin, or?
Well, yeah, I mean, it's an ellipse centered at the origin, but it's effective for any ellipse as long as you know the length of the major and minor axes, right? Because, this ellipse, you find the length of the major and the minor axis by taking that a and that b value and just multiplying them by 2. So if you know that it has no matter where it's centered, if the length of its major axis is 12,
Oh, right.
then a would be 6, and if the length of the minor axis is 8, then b would be 4. And so you just use it that way.
Right. Okay. Thank you.
Isn't that exciting? Aren't you all just amazed and astounded by what calculus can do?
And isn't that also the area of a circle?
It is,
and B.
exactly. Yes, because a and b for a circle, I mean, a circle is just a special ellipse, right? Where a and b are equal to each other, and it's the same, pi r squared. Yep.
That's fascinating.
Isn't it fascinating? It's amazing how math works out, right? It's just like all these things are interconnected. The mysteries of the universe. Oh, very exciting. Any questions on anything? Or should we continue to unravel the mysteries of the universe?
I'm down to continue to unravel the mysteries of the universe.
Wonderful. This one is probably, I don't actually remember what's next here, but probably less of a mystery of the universe here. the definite integral from 0 to 3 root 3 over 2 of x cubed over 4x squared plus 9 to the 3 halves. Ah, yes, that's right, Derek. This is why I am a good spiritual advisor. Yes, because of my calculusing ability.
Calculus has all the answers to your problems.
I don't have any problems, but thanks.
The general you know, just anybody.
Perfect. That's good. It does, really. Yes, the mysteries of the universe, the problems of all mankind can be solved using calculus. This is true. So what should we do with this next one? This one looks annoying, doesn't it? The correct answer is yes, it does. Why does this one look so annoying?
There's like a bunch of powers and constants that just don't work together nicely. They don't.
Yeah. To start with, if we look at this here, instead of it being, oh, that was horribly circled. Instead of it being x squared plus 9, it's 4x squared plus 9. So that normally we just do this substitution where, like, you know, x would be, if this was just x squared, we'd say, oh, okay, great, x is 3 tangent theta, right? Because I told you guys if it's 3 halves power, we could still try and use that method. But it's 4x squared. So really, I can't let x equal 3 tangent theta. I have to let what equal 3 tangent theta?
Two x?
Yeah, 2x, because this effectively is 2x squared plus 3 squared, right? And so I could, if I wanted to start off, let's say, all right, let's let u equal 2x, and then get this to be u squared plus 9 down here. But it seems simpler to not do a double substitution here. It seems simpler to just let 2x equal 3 tangent theta and deal with the constants up here with our x cubed dx's. Right? Because if I let u equal 2x to start with, then I gotta, like, you know, gotta put in a 2 up here and put in a 1/2 out here and change my limits of integration and all that nonsense. It seems easier to just start off with 2x equals 3 tangent theta. And if 2x equals 3 tangent theta, then this ought to become, in the denominator, what?
Nine tangent squared theta plus 9, the 3 halves power.
9 tangent squared theta plus 9, all raised to the 3 halves power. And then in our numerator, we got to figure out what x is. So, well, if I divide this by 2, x is 3 halves tangent theta. Right? And so what is x cubed? X cubed ought to be ought to be 27/8. So let's just put that out there to begin with, because I don't want to deal with that. 27/8 tangent cubed theta. And then what is dx? Dx is 3 halves secant squared theta d theta. So tangent cubed theta secant squared theta d theta. And then we got another 3 halves to throw in outside of here. So 27/8 and a 3 halves. Good or no? So far. Still got to do one more thing here before this integral is complete-ish. But good or not good?
Yeah.
So yeah, quick question. The 27/8 came from x cubed. So x cubed means we're cubing this 3 halves tangent theta. So that's 27/8 tangent cubed theta. And I just put the 27/8 out in front. Okay, cool. Last thing we had to do then is figure out our new limits of integration. So x was 0. So if x is 0, what do we end up with? We end up with tangent theta equals 0. So what would theta be? when x is 0?
0.
Should be still 0. Okay, good. And then we also have to say, what about when 3 root 3 over 2 equals 3 halves tangent theta? The 3 halves will both cancel, and we have root 3 equals tangent theta. And what does that give us? Theta equals pi over
3.
3. Good. All right, so we have effectively 81/16 the integral from 0 to pi over 3 of tangent cubed theta secant squared theta over 9 tangent squared theta plus 9 to the 3 halves power d theta. So let's make that look nicer. So first off, no constants in the numerator, correct?
No constants in the numerator.
That's good news. So 9 tangent squared theta plus 9, you can have a 9 factored out of it, right? And if I pull that 9 out of the 3 halves power, we have to square root it first, which gives us
3.
3, and then cube it, which gives us 27. So that'll cancel with the 27 here. If it's a 1/27th, it's a 27 in the denominator. So our new constant out in front ought to just be 3/16. Good or no?
Yeah, that's better.
All right, 3/16, the integral from 0 to pi over 3. And now if we took the 9 out of there, this just became tangent squared plus 1, which is just secant squared, right? And if we square root secant squared, that's secant. And if we cube it, that's secant cubed. So that'll cancel partly with the secant squared. So we're going to have tangent cubed theta over secant theta d theta. Good or not good?
Not good.
Okay. And then what should we do from there?
Can we put it into terms of cosine and sine?
So 3/16, the integral from 0 to pi over 3. And now let's see, this is sine cubed over cosine cubed over 1 over cosine. So what should that become? It should become sine cubed theta d theta over cosine to the second power.
Yep.
Okay. All right. It's getting worse and worse. Now what? I mean, it got better, but then that looks worse than that, maybe. What should we do with it now?
I don't know, maybe like tangent squared theta over. Oh wait, no.
Now let's just leave it in the form we got in with the sines and cosines now.
You sub the
You sub what?
cosine.
All right, if u is cosine theta, then du is negative sine theta d theta. Yeah? Everybody agrees with that? Yes, no, maybe? In the numerator, I've got a sine theta, right? Which is going to need a negative attached to it. So I'll put a negative inside and a negative outside. And then what's left in the numerator is a sine squared, right? But having an extra sine squared in there is not going to let me convert everything into terms of u. But I could rewrite sine squared as 1 minus cosine squared, couldn't I? So we went from sine cubed in the numerator to sine times 1 minus cosine squared, and then we threw the negative in with the negative outside to let our u substitution happen. Everybody good with that or no?
Yeah.
All right. So now the only thing we have left to do is to convert this into terms of u, which should give us negative. Sorry, we should continue writing. What were these limits? It was 0 and pi over. What is it? Pi over 3 up there, I think.
Yes.
So negative 3/16, and now it's an integral of, let's see, well, that becomes u squared in the denominator. And what else do we need to do with this? Negative sine theta d theta is our du, and 1 minus cosine squared is 1 minus u squared. And we got to convert this 0, which is a theta, into u. So cosine of 0 is 1. And then cosine of pi over 3 is 1/2, right? So convert that into a 1/2. And from there, how do we deal with this integral? First off, I'm just going to flip my limits of integration from 1 to 1/2 to 1/2 to 1, and then get rid of the negative sign. And what can I do with 1 minus u squared over u squared?
Just divide each element in the numerator by u squared.
All right, so u to the negative 2 minus 1 du, which should give us 3/16. And the integral of u to the negative 2 is just negative 1 over u. And then the integral of 1 du is just u. And we're going to evaluate that from 1/2 to 1, which shouldn't be too bad. 3/16 times negative 1 minus 1 minus, and then negative 1 over 1/2 is negative 2 minus 1/2. And that should all simplify down. Let's see, negative 2 plus 2 will cancel out, right? And then we have negative 1/2, which is 1/2. So we have 1/2 of 3/16, which is 3 over 32. Good or no? Any questions there? Any issues there?